Welcome back. Today we'll be talking about linear systems and vector spaces that have to do with them. So when we're performing Gaussian elimination and its row operations, what we're really doing is taking linear combinations of rows. And so it makes sense then to study the vector space in which they exist, and that's called a row space. So if I have a matrix A, then the row space of A is the span of its rows, and the dimension of the row space is the row rank. So row space is the vector space, row rank is the dimension. Just to make it clear, if I have this matrix A with these rows, then the row space is the span of the set of rows, some scalar times the first row, plus some scalar times the second row, plus some scalar times the third row, where each of those scalars can be any real number. And in the case of this matrix called B, the row space is just the span of the rows, but you'll notice that the second row is actually -2 of the first row. So the rows are a linearly dependent set, therefore I could simplify the row space to the following. It's the same if I just call that set the span of the first row only. Here's something to know. If I have a matrix A and through Gaussian elimination and row operations it reduces to matrix B, then we call those matrices row equivalent. And you can think about it, equivalence is sort of two-sided because row operations are reversible. So if I can reduce A into matrix B, then I can also take B back to A. And if this is true, then these matrices will have the same row space and therefore the same row rank as well. And here's why. The row space of B consists of these rows, let's just call them R for example. I have one row in the row space of B called R. And if it's in the row space of B, it means that it's in the span of the rows of B. So it's some linear combination of the rows of B. Say some amount of RB1 plus all the way to some amount of RBM. So we have M many rows in matrix B, for example, and I'm taking some linear combination of them. Well, how did we get each of these rows in B? We got them from row operations on matrix A. In other words, each of these rows are themselves linear combinations of the rows of A. Therefore, R, which is equal to a linear combination of the rows of B, is really equal to a linear combination of linear combinations of the rows of A, which is just one linear combination of the rows of A, so it's also in the row space of A. So we've shown that the row space of B is contained within the row space of A. We could perform an analogous argument because of the fact that row spaces are reversible. We imagine going from B to A, and we look at some element that we could also call R in the row space of A and show that it's in fact a linear combination of the rows of B, so it's in the row space of B. And if both of those row spaces, both of those sets, are contained within one another, then that means that they are equivalent sets. The matrices have the same row space and the same row rank. So now we're just going to prove a lemma a bit more formally. So this one says that if I have a matrix in echelon form, then its non-zero rows form a linearly independent set. So if I label these R1, R2, all the way to Rn, I'm going to cast each of these non-zero rows into column vectors. So row 1 as a column vector would look like this. 1, 3, 0, etc. I just chose random entries for this row. And so if these rows are linearly independent, then the only linear combination of them that should be equal to the zero vector is the trivial combination. And you'll notice I've displayed and indexed the components here so that R1, 1 means the first component of the first row, and that R1, n means the first component of the mth row, and so on. So the first subscript represents the position in the row, and the second subscript references the actual row it's a part of. The first row, the first equation of this linear system right here, says that a bunch of constants multiplied by the first entries of each of the rows in the matrix is equal to 0. In other words, C1 times the first entry of the first row plus all the way to Cm times the first entry of the mth row is equal to 0. But if we look at this row echelon form matrix, all of the first entries of each of the rows in the matrix make up the first column of the matrix. In the first column, because this is in row echelon form by definition, the first entry is going to be a 1, and all of those below it are going to be zeros. In this last part of this linear combination down here in red, all of the r's are going to be zeros, because that's what all of these green zeros are here. And we know that the first entry of the first row, or in other words R1, 1, is just equal to 1. So this right here, this equation says that C1 is equal to 0. Why is it important that we show that C1 is equal to 0? Well, we assumed that this matrix was in row echelon form, and now we're trying to demonstrate that it's linearly independent. That is, we're trying to demonstrate that the only linear relationship of this kind right here is the trivial kind. C1 all the way to Cm all have to equal 0. So we have to first demonstrate that C1 is equal to 0, then that C2 is equal to 0, etc. So now if we look at the second row of this linear combination, it says that some constants times each of the second entries of each of the rows in the matrix is equal to 0. If I multiply all these constants by and then add together all of the elements in the second column of this matrix, then that should be equal to 0. So C1 times R2, 1 plus C2 times R2, 2 plus all the way to Cm times R2, m is equal to 0. Well, we know that C1 is equal to 0 already, So we know that this first term is just equal to 0. And if we look at the column up here, we don't have to count the first entry anymore because C1 is equal to 0. All of the elements that come after R2, 2, that come after the second entry of the second column, are equal to 0. And so this remaining part of the linear combination goes to 0 because all of the r's are equal to 0. R2, 2 is just equal to 1. And so we find that the next scalar in our linear combination is equal to 0, that C2 is equal to 0. And we can just keep doing this all the way to Cm, which we find is equal to 0. All of the coefficients, all of the scalars in this linear combination of the rows of the matrix are equal to 0, which means that the only linear relationship of this kind is the trivial relationship. So the purpose of that prior lemma was to show us that, again, Gaussian elimination gets rid of the redundant rows, and we finally understand what redundant really means, because I believe I mentioned that before, and that is it gets rid of the linearly dependent rows. Those become rows of entirely zeros. And so because of this, we can use Gaussian elimination to find bases. So let's say I want to find the basis for the span of this set. It consists of these three vectors. Well, I'm going to cast these three vectors into a matrix. The first vector is going to become the first row. So it becomes the row 3, 2, 1. The second vector becomes the second row, -1, 0, -2. And the third vector becomes the third row, 4, 2, 3. Now I'm going to perform Gaussian elimination on this matrix, which yields 1, 0, 2, 0, 1, -5 halves, 0, 0, 0. And that's actually reduced row echelon form. This third row is a row entirely of zeros, which means that we had a linearly dependent set. This set had a redundant vector in it because any of the vectors in this set could have been expressed as a linear combination of the other two. By getting rid of one of them, I have a linearly independent set. And so we can take the first and second rows back to column vectors and we get a basis. Our basis is equal to the set of the vectors 1, 0, 2, 0, 1, -5 halves. So just as we had the row space and row rank, we also have column space and column rank. The column space, analogous to the row space, is the span of the columns of a matrix, and the column rank is the dimension of that vector space. So here's an example. I have this matrix A, it has 3 rows and 4 columns, and the column space is the span of these 3 column vectors. Now, if I want to find the basis for this column space, I'll write the columns of this matrix as the rows of another matrix. And this other matrix has a special name. It's called the transpose of this original matrix A. So the transpose of A is equal to the matrix where the first column becomes the first row, the second column becomes the second row, and so on. And this is what that would look like. I then take this matrix to reduced row echelon form. You'll notice I have a redundant row of zeros right here. And then I transpose it back. And this column is going to be our first basis vector. And the second column is going to be our second basis vector. And this third column consists entirely of zeros, so it will not be included in the basis. So the basis for the column space is the set of these two vectors, 1, 0, 2, 1, 0, 1, -3 halves, -1. Finally, it's important to understand a bit about row space and column space. Row operations don't change column rank, and that's because row operations don't affect the linear relationships among the columns of a matrix. Recall from, I think it was one of the first videos, that when we perform row operations, we don't change the veracity of the equations that make up our linear system, or in other words, the rows of the matrix. Row rank and column rank are actually both the same thing, and that's just called the rank of a matrix. And because of this, I can create a basis for the row space of matrix by isolating the non-zero rows of that matrix in echelon form. So these two rows create a basis for the row space. And similarly, I can isolate the columns with the leading entries in them. Those are the leading ones in each of these rows, these ones right here, to create a basis for the column space. Now, the reason why the column basis can be constructed this way with the same number of column vectors as there are rows for the basis of the row space is because these two columns are actually both members of the standard basis. Now, you won't necessarily have all members of the standard basis. This one, for example, is the vector E1 or I hat in the standard basis for R3, and this vector is E2 or J hat. And these vectors are not only linearly independent, but they span all the other vectors in the column space. For example, the vector 3, 0, 0, the second column of the matrix, is just 3 of E1, and the vector 1, -1, 0 is just 1 of E1 minus 1 of E2. And so both of these are linearly independent and span the column space, therefore they're a basis for it.